Hey there, folks. How you doing? And we are back for the final installment, finally, right, of energy in the atmosphere. Okay. So we left off. We were talking about Wien's law, and really, what Wien's law explains to us is the connection, the relationship between surface temperature. Of something like a star or any object, really, and the wavelength of color that it emits. Okay, remember it's subtle, but it's in the background. We're really trying to make this connection about energy and matter and mass all sort of being the same thing, and that these wavelengths of energy, which we call light, or even, the kind of light we can't see, the ultraviolet, the infrared, so on and so forth, are functions of temperature, okay, which again are energy levels. So, and then again, it's matter itself that is vibrating at this level, at this speed. It's big. It's a big idea, okay? It's a big idea. So if you find yourself kind of mucking about in it, you're not alone. Really don't be concerned about taking all this philosophically, at any rate, beyond the superficial presentation that you're getting in this PowerPoint. But it certainly is a much bigger topic. If you feel like you're missing some stuff, that's certainly true. And it's one of those things where the more you grasp, the more you get confused, unfortunately. But just bear with it, and remember that I'll keep things fairly civil with regards to questions. So I think we saw these two slides already. It's been a while since I recorded this part in the part before it, but the sun, we want to remind you, of course. You're not supposed to stare directly at it or stand out in front of it too long. That's not because of visible light, okay? That's because of the other wavelengths, the other spectrums at which it's emitting. But one of the wonderful things we do get from it is visible light from 0.4 to 0.7, right? 44% of its light, as a matter of fact, comes off of there. And just in case you were wondering, it peaks right around the blue-green spectrum there. And here's the breakdown, a little more information in case you wanted it. I'm not going to, I didn't even talk through this slide. I'm not going to hold you guys, to these numbers, okay? But we've talked about ultraviolet and infrared already. You know that those are there. Those are given off. You might not have thought that these were given off as well, but they are. And these are, remember, your longer wavelengths here. We've been dealing with visible ending at 0.7, right? So we're almost double that up here. So there's 12% is long wave radiation as well. You can go back to the spectrum chart if you want to see what's up there. Okay, the Earth, because of its temperature, I think we already mentioned this, the Earth does not radiate visible light. Okay, it's not hot enough. Thank goodness we wouldn't be here if it was, okay? So all the picture like this, any picture you've seen of the Earth, is reflected light. Our energy is given off in the infrared spectrum. Now, the thing about the Earth is, and any radiator, really, any radiating body, is that it is always giving off energy. Right? It's not like the heater in your car or your house where you could turn it on and turn it off. It's always losing. Think of radiating in this case as losing. It's always losing energy. It's always giving off energy. So if it's always losing the system, we'll call the Earth a system for a minute. If it's always losing energy, well, why isn't it getting colder? Well, that's because, as you hopefully figured out, it is also absorbing energy as well. So the whole Earth radiates all day, but during any given time of the day, half of the Earth is absorbing energy. All right, it's bothering me. I got to fix these capital letters here. I missed them when I was redoing this. Sorry. There it is. So yeah, okay. And if you're thinking about, well, wait a minute, if the whole Earth is radiating and only half of it is absorbing, that sounds like a losing battle. And you're absolutely right. It would be if it weren't. Okay, for something that's a slider two off still, sorry. But yes, you're right, it is a losing battle. Okay. All right. So what does energy absorption depend on? Energy absorption depends on a handful of things. You probably figured this out fairly early in life. The blacktop out in front of your house is a lot hotter than the grass. The sidewalk is hotter than the grass, but cooler than the blacktop, and so on and so forth. The black leather seats in your car or your friend's car or whatever are going to be hotter than the white leather seats, and both of those are hotter than the cloth seats. All right, not everything absorbs the same way. These are some factors. Again, we're just talking about this loosely right now, introducing the idea that there is variance. I'm not worried about these details here, okay? But just understand that there is variance. Because what we want to talk about is this idea, black body, okay? A black body is a perfect absorber and a perfect emitter. And it doesn't necessarily have to be black. All right. The Earth and the Sun are black bodies. This word "perfect" here is again could have a whole PowerPoint in and of itself. Let's just say you could substitute "really good at," okay, for the word "perfect." All right. Remember I told you it would be a losing battle if it weren't for, yeah, here's that slide now. Thank goodness, okay, our atmosphere. And thank goodness not everything is a black body, okay, because it would take in and give off everything that it gets every moment of every day. And again, it would be tough to warm up, okay, or cool down for that matter. Thank goodness for our atmosphere. Okay. A selective absorber is not a black body. Okay. Selective absorbers and black bodies are different things. A selective absorber can absorb some things better than others, or not absorb some things at all. Okay. So here's the first one. A selective absorber can absorb some wavelengths more than others, and then some of them not at all. Pass right through. Some bounce off. That should probably be its own bullet, huh? Instead of a comma. Yeah, we'll make that its own bullet. So, as I said, luckily for us, most objects are selective absorbers. They only absorb certain wavelengths of radiation. A neat example of this one is glass. Glass can absorb infrared and ultraviolet, but it lets, guess what, through? Yep, visible light. Okay. Kind of handy that way. What else? Let's not talk about something man-made like glass that we could add the infrared and the ultraviolet stuff to. let's talk about something natural. Let's talk about greenhouse gases. All right. And we haven't really talked about greenhouse gases a whole lot. You have, just from living in the world, you have some indication that greenhouse gases are these things that are up in the atmosphere, and let me guess what else you know, that we've got too much of them, or at least half of the country says we have too much of them, and it's because of that we're going to hell in a handbasket, right? Well, greenhouse gases are real things. They're important things. I'm going to say Mother Nature does something. Forgive me there. Mother Nature has, kind of sets up the system the way she likes it to run, right? we can put all this in that perspective momentarily, just conversationally, if you wouldn't mind. So Mother Nature has set the level of greenhouse gases for what works great at the moment. What at the moment being we're not glaciated, okay, and like ice age glaciation, but yet we still have some ice caps all throughout the planet. We're going to just call that normal, okay? We'll call a completely, an ice age state one end of the spectrum, and no ice anywhere the other end of the spectrum, okay? So right now we're kind of not exactly in the middle, but we'll happily in the middle, all right? We'll call that normal. That is because of the balance of gases in the atmosphere, all right? And we've gone into and out of these ice age time periods several times, all right? And we have records, gas bubbles, air bubbles. We talked a little bit about this in the history of conservation lecture. And we have air bubbles that show us, these records, and we could run simulations on computers now, and so on and so forth. And a lot of that is dependent on the greenhouse gas levels. We'll just pick one. There's several, but we'll just pick one. We'll pick carbon dioxide. That's the one that everybody hears about, okay? We could see in our air samples that when CO2 levels go really, really low, ice tends to grow, okay? Climate changes to a colder climate, and giant glaciers form that go from the North Pole all the way down to, New York State, for example. It's pretty honking big hunks of ice, right? And then we can also see on the other end of that and when that happens, of course, what do we talk about? Sea level goes down, right? Okay, because you have to pull that water from somewhere to make those glaciers and make all that ice. And then on the other end of that spectrum, when CO2 levels go really, really high, we see that all those glaciers recede, go back to where the ice is supposed to be, you could say, and we see sea level go up. Well, the trajectory is, the implication is, of course, is that if those CO2 levels continue to go up, that ice will recede even more and sea level will go even higher. That's the drama scenario that you're hearing about all over the place. All right. And it is a potentiality for sure. So that's the context that you've heard, if you've heard anything, that's the context that you've heard about greenhouse gases. What you hardly ever get to hear is that we really, really need greenhouse gases. We love them. We want them. If we did not have them, okay, this planet would be a lot colder. All right, as I could kind of just implied, but so anyhow, I kind of went off on a tangent just to give you a little background, but what's on the slide actually here bears telling as well. Okay, greenhouse gases are selective absorbers, and if you get into this, carbon dioxide isn't even one of the worst offenders. It's just people feel one of the easiest to control, or easiest to point fingers with. Okay, there are definitely methane is another big important one. Heck, water vapor is a greenhouse gas. Okay, you don't see anybody yelling about the water vapor in the atmosphere. But carbon dioxide comes from burning fossil fuels, or excess carbon dioxide comes from burning fossil fuels, and so on and so forth. So, like I said, that's an easy finger pointer there. Anyhow, the idea, and we'll stick with CO2 for a minute, is that remember we told you that the Earth emits infrared radiation all day long and all night long, right? Well, the CO2 and a handful of the other greenhouse gases trap that infrared radiation. They stop it from leaving the planet completely. They hold that into its atmosphere. And as I said, that is a good thing. We want some greenhouse gases, all right? Just not a lot. Just not a lot. And again, Mother Nature has it set rather nicely. Whatever the levels of CO2 and methane and water vapor and everything else out there, okay? Whatever those levels are, and again, this class isn't about memorizing those numbers, but it is about understanding that whatever it's set at right now is responsible for the climate that you currently see on this planet. And when you change those levels one way or the other, it will directly change the climate that you see. So I said this here. And I think the only thing we didn't mention is this bottom bullet, that they could also bounce some infrared back at us. Another capital E, forgive me. So, I told you we need some. Here's an actual number for you. And again, I'm not going to quiz you on it. Is it 0 degrees Fahrenheit, 5 degrees Fahrenheit? No, it'd be a lot colder. All right, the average surface temperature would be 0 degrees Fahrenheit. We would not appreciate that. So we want some CO2, okay? We want some. All right, you guys. So, thank you for sticking with me through all this. It's been a rather long and probably, I agree, one of the more difficult conversations we've had all semester and will have all semester. This is some tough science. So if you have any questions, again, you certainly can check this out in your textbook, okay? But by all means, shoot me an email, and I'll either explain the heck out of it, or try to at any rate, or tell you, hey, you don't need to take it that deep. Don't worry about it. But here's a little bit of explanation kind of thing. So please, I always tell you guys, feel free to ask questions. But as I said, this is a tough chapter. Take care. Be well.